Okay, so first of all, thank you very much for very kindly inviting me to give a talk in this international conference. And I would especially like to thank Dr. Aisha Khalid. So today I will be talking about the dynamics and multiqubit entanglement in distant resonators. Okay, just to give you an idea of our research group. So currently we have two very young and very brilliant fellows, Dr. Irfan and Dr. Asim. Then we do have visiting scientists and then his graduate students. And we also enjoy research collaborations with Professor Moro in Belfast and colleagues in China. Okay, so I'll be talking about the dynamics of the interacting decay model in a coupled cavity array. So it was published in Physical Review A back in 2014. So let's ask this question, what is the decay model? So the decay model is a fundamental model of quantum optics, which describes the interaction between light and matter. Right? In the decay model, the light component is described as a single quantum mode, while the matter described as an N2 level atom. I hope, so please notice this point, that we have interaction of the light single quantum mode with the matter, which consists of N set of 2 level atoms. Typically, we talk about interaction between single atom and the radiation field. So here we have ensemble, right? Okay, so here is the schematic of the system. Now, please notice that we have these 3 cavities, right? And then there is this ensemble of 2 level atoms. And then we have hopping between these cavities. Right? So this is something interesting. So what we would like to see how initial field in one of the cavity goes to other cavities, right? So here I've shown 3 cavities, but the system can be expanded to N cavities in principle. And for the sake of simplicity, we'll be focusing over here in one dimension, right? But it can be extended in 2 and 3 dimensions. So the key point which I would like to again emphasize that we have ensemble of 2 level atoms between the inside the cavity, and then these cavities are interacting with the neighboring one through hopping field. Okay, I think whole my talk can be explained through this coupled oscillator, right? And all of the stuff that I will be talking about is basically in this simple picture. So we have this famous coupled oscillator, which I'm sure every undergraduate student has gone in its physics course. So we have 2 pendulum hanging from a string, which is an example of pair coupled oscillator. Now, please notice that there is a shift in the amplitude from one pendulum to the other in time, right? So for example, this red pendulum start oscillating, and then due to this coupling, it goes to the red, green, then it comes back, and so on. So notice in the red, we have this oscillations, then they go damping out, and in the green, it shows when the 2 are both oscillating. So you can consider one to be atom and other to be cavity field. Remember, if you have ideal system, so these oscillations will continue forever, but it never happens. Eventually, it dies down, right? So eventually, the 2 pendulum will stop. You can consider different initial conditions. For example, green is stopped, and you bring red up to some point and then release, right? And you can do vice versa. So my point is, all of the dynamics that I'm going to discuss is basically what we can see in this coupled oscillator. So keep this picture in mind. But this is the simplest way of explaining cavity quantum dynamics. Okay, so I would like to avoid equation as much as possible, but I think you must give this Hamiltonian, the mean Hamiltonian in the interaction picture. So here the first term and its conjugate is nothing but the tunneling of photons, which is represented by this J between adjacent cavity. And the second term and its conjugate is in situ resonant exchange of excitations, right? So through Wi is basically responsible for this resonant excitation. Okay, these S plus minus are the decay operator of the atom within the cavity, and sigmas are nothing but the single atom cavity ladder operator. A and A I got nothing but the field operator. So I think this will be the only equation that I will show. Okay, so now let's look at the result. So the first case is comparable hoping. I'm sorry, I mean, this top is not visible to me. Let me adjust. Okay, so yeah, I cannot see the top there. Okay. Anyhow, I will try to. Anyhow, I will try to explain from here. Okay, so is it visible to everyone?
Mm-hmm. Yeah,
okay.
We can see.
So, okay, so the first case that I will be talking about is comparable coupling and hoping. Notice that we have coupling of the ensemble with the field which is in the cavity, and then we have hoping between different cavities. So we could talk about different scenarios, whether these coupling and hoping are same, coupling is weaker than hoping, and vice versa. So the first case that I'm considering is when coupling and hoping are comparable, meaning J over omega is equal to 1. Now, see the first picture. It shows the first cavity, right? And we assume the 3 cavities to be initially in the vacuum state. And we have single excitation in the first cavity, meaning the ensemble of the first cavities, they are assumed to be in the excited state. And now recall this pendulum problem. This excitation will go to the second pendulum, and that's exactly what is happening. Excitation is going from first to second cavity, right? So, and one more thing, the number of atoms in the ensemble over here is 10. We assume 10 atoms or qubit in the ensemble. So from first cavity, it goes to the second cavity, and then it goes to the third cavity, right? So this will continue forever because we have not assumed any losses in the system. Okay, what about the excitation between the ensemble? So basically, this picture D shows excitation transfer to cavity 3 from cavity 2, which induces excitation in the ensemble 3. So this reverse process will take place, which eventually lead to the excitation of cavity mode 1 and then the corresponding ensemble. So this process will continue forever. So let me again repeat that this picture A shows the first cavity evolving in time. So the excitations are, the oscillations are decreasing. So it is hopping in the second cavity, and then the second cavity is interesting because it is connected with the first and third cavity, right? So we have oscillation, a damping, and then again oscillation, and that it eventually goes to the third cavity, and then it will bounce back and forth, and the whole process will continue. In the D picture, basically we show the dynamics of the ensemble, right? So that remember this red shows ensemble 1 that was in the excited. So again, its excitation goes to the ensemble 2 and 3, and this process will continue. Okay, let's see something something even more interesting behind the excitation. You know, what I talked about so far is in line with what we observe with the pendulum, right? But in quantum mechanics offer us another possibility, and Dr. Shahid already talked about it and talk about this entanglement. So I don't need to really explain it, because this entanglement is something which is perhaps one of the most amazing things in quantum mechanics. So this system also exhibits entanglement of the ensemble. Now notice that these ensembles are in 3 different cavities, but they evolve into entangled state. So here I have written down this W state, which is nothing but 1 over the root of 3, 0, 0, 1, plus 0, 1, 0, plus 1, 1. Notice we cannot write down this W state in product form. So now look at the figure. Again, we are showing the probability of excitation transfer versus time for the ensembles. And here we have formation of W state at time is equal to 0.55. Notice at T is equal to 0.55, we have excitations in all 3 cavities, right? So these cavities are prepared in a beginner state, and there is no classical analog for this thing. That I must emphasize. We can't see this behavior with a classical pendulum, which is purely quantum mechanical feature. Okay, next we come to the large hopping case, right? Meaning hopping is much larger than omega. Omega is the coupling between the field. So first figure shows the cavity mode, and second shows the ensemble. Again, 3 cavities are initially in a vacuum state, and single excitation in the first. Now notice that, let me mention here that solid red shows excitation in the first cavity, thick dashed line shows excitation in the second cavity, and thin dotted line shows excitation in the third cavity. Notice cavities have a small probabilities of excitation. The value in picture A goes up to 0.35, right? And the reason is obvious, because now hopping is dominating here, right? So initial excitation in the ensemble 1 has transferred 100% to the 3. Look at picture C, which shows the ensemble. So hopping is dominating. So all the excitation of the ensemble goes to the ensemble in the neighboring cavity, while the cavity fields are evolving, but obviously, and they have very small probabilities. Okay, now let's look at the second case when we have a strong coupling, right? Meaning, now in this case, coupling of the ensemble with the cavity field is stronger than the hopping, right? So 3 cavities are initially assumed to be in vacuum state, a single excitation in the first cavity, and the number of ensemble are 10, right? So you can play with this thing. You can have 10, 20, and so on and so on. Look at the first cavity. There is a rapid transfer of excitation. Very quickly it is going to the second. Very quickly there is transformation of the ensemble into the local field. The reason being, hopping is weak, right? So ensemble is interacting with the cavity field and transferring it to the cavity. And as a result, we have very fast oscillations. So the 3 cavities are again coupled weakly, but obviously they are connected. So we start with the first cavity, then we have in the second cavity, we have again these oscillations. It goes eventually to the third cavity. And now if you look at the dynamics of the ensemble, again, we can see excitations are going into the neighboring one. But here the dominating process is ensemble coupling with the local field inside the cavity. Okay, please notice that so far I talked about the exact resonance case. So if I go back to the pendulum problem, right? What I mean by resonant? Resonant means the time period of the two are same length. But now if I want to explain classically how to make an analogy for the non-resonant, I have to take 2 pendulums of different lengths, right? And recall the first picture that I showed. Now keep this thing in mind. So here we are introducing a detuning, meaning the field is detuned from the cavity. Okay, again the same system. We have field inside and then hopping through this lambda. Okay, please. I was using different parameters. Earlier we have used J over here lambda, so but don't worry about this thing, right? And lambda is showing here the hopping between the 2 adjacent cavities. Okay, intuitively, without doing any calculation, what we will be expecting? Obviously, we will be expecting that due to detuning, excitation transfer is delayed, right? So here, first figure shows the case when we have exact resonance. Again, 3 cavities are in the vacuum, and the single cavity in the first cavity, excitation in the same. Meaning we have some field in the first cavity, and then second and third are empty in terms of the ensemble. Notice the 2 things. Field inside the cavity, which is vacuum, empty, but we have ensemble. So the ensemble of the first cavities are excited. In this case, we are taking the ensemble to be 10. It means we have 10 atoms, or you can also call 10 qubits if you talk in terms of the quantum information language. Okay, cavity modes, solid red, orange thin, large dash black, and small dash, they are all shows cavity modes. While the ensemble is shown in solid thick red curve. Please notice, in this case, I have plotted all the 3 modes and the ensemble in one picture in A, right? Now notice, when we switch on detuning, here delta is 10 gamma. It is scaled in terms of the coupling. Chi is nothing but the coupling. So excitation is delayed as compared to the case when we have delta is equal to 0. And that is what we were expecting, right? Okay, now the next question is, still we get entanglement? I mean, this W state. So let's see. So over here, again, 3 cavities are in vacuum. Single excitation in the first cavity and the qubits are 10. Notice we have formation of W state at T is equal to 5.7. Look at this inset, right? So at 5.7, all three are overlapping. There is a point where the three are overlapping. It means the three cavities are now entangled. You can always ask, what about the field inside the cavity? Ensembles are entangled. What happens to the field? So look at the picture C. This shows the population in the cavity mode, and exactly at 5.7, all the cavities are almost empty. This is something very, very interesting. So ensembles are entangled to each other, while the cavity field is all in the vacuum state, right? So what I want to emphasize that in the presence of detuning, first of all, there is a delay in the transfer of the excitation, and second, we still obtain the formation of beginner W state, right? Okay, this picture shows a comparison for the delta zero and delta non-zero for the generation of W state. So again, three cavities are in the vacuum state, and with single excitation. Yeah, one difference here. Okay, again, earlier we have used first cavity in the excitation. Now, second cavity is excitation, meaning if you have three pendulums, right, and the first and third are stationary, while I bring the second pendulum to some height. That is what I mean by excitation, right? So I bring the second pendulum to some height and then release. Notice second pendulum is coupled with 1 and 3. So I mean, excitation will go into the two side. So here we take the cavities to be in the vacuum, and single excitation in the second cavity. We have three cavities, and the second is in the excited state. Number of qubits are assumed to be 5, but as I mentioned, you can increase it. Nothing wrong. Now notice delta is equal to 0. Look at this purple graph. So we have, I mean, this shows the population is going in the two cavities, right? Excitation is transferring. But here, entanglement is obtained. W state is generated at t is equal to 0.5. Notice at t is equal to 0. All three are overlapping. Here we are plotting the excitation transfer for ensembles, right? From the middle ensemble, excitation is going to the right and the left, and W state is formed at t is equal to 0.5. Now see what is the effect of detuning. When we introduce detuning, which is in this case 20 chi, I'm sorry, we still obtain W state, but it is at two different times. At t is equal to 3. Now look at the picture B, 3, and at 7, right? So at 3, all these are overlapping. At 7, they are overlapping. So what we can conclude, meaning for the case of resonant, if we are doing the experiment, looking at the system, its evolution with time. So at t is equal to 0, we'll see the W state. However, if we introduce detuning, then we'll see the generation of W state at two different times. One more thing which we must notice, that it is not that this system will exhibit entanglement for any value of time, right? At some time, system will become entangled. That is something very, very interesting. So it means if we are doing experiment interested in W state, we need to take care of that time particular. So from this study, we are predicting that choose such and such value, such and such interaction time, and you'll get the entanglement or W state. It is not for all time. It is how the system behaves. Okay. So to summarize, introduction of detuning allow you a possibility to obtain W state at two different times for this particular case. Right? Okay. You know, so far we talked about the cavity array, which is nothing but typically consists of superconducting cavities, and then they are coupled. This goes back to the seminal work of late Professor Walther and Professor Harros, who eventually got the Nobel Prize. But you know, in recent years, there's also a lot of interest in artificial atoms, right? So you know, we have flying qubits. So for example, these photons, they're flying qubit. Cavities are stationary qubit. And then in recent years, people also got interested in this artificial atoms, right? And the dream is basically to do quantum optics on a chip. Right? So next, we discuss the same problem, but in an artificial atom. So this was published again in last year. So the system looks like the following. Now we have circuit quantum electrodynamics. So it consists of n superconducting resonators, R1, R2, R3, and so on. These are the Now, superconducting resonator. Please notice they will be on a chip, right? They are coupled to a common superconducting resonator bus, right? Red one, through some coupling G. And then the common superconductor, this common resonator act as a bus. And then here is superconducting resonator RJ, through which we can catch or release a photon. You know, we would like to have, for example, in cavity, if we would like to have one photon, we need to do some experiment. We need to send atoms that will emit and contribute a photon. Now, in superconducting resonator, you must have a resonator from where you can catch. So basically, this TL is nothing but a transmission line through which we can catch or release a photon. So, for example, if you want to have one photon in R1, nothing in R2, nothing in R3, so we need to catch one photon from R1, nothing from R2, nothing from R3. So the state will be 1, 0, 0. Now keep this picture in mind. And now let's see how the excitation transfer takes place over here and how is there any possibility to still generate W state. So here we consider the system to be initially in state where one photon in resonator 1, nothing in, by the way, here I'm considering 4 resonators, right? And 0, 0 is the bus actually. So one photon in the first resonator, nothing in the second, nothing in the third, and nothing in the fourth. Now notice over here we have shown the time evolution of the photon population if 5 resonator. When I say 5 resonator, it means 4 resonator R1, R2, R3, R4, and the 5th one is the bus resonator. All of them are connected with it. Now the horizontal dash line, basically this marks the point. Notice P1, P2, P3, P4, they are the population of the photons. So this horizontal line shows the point of intersection, right? And at this particular point, we have W state, 4-qubit W state that is generated here. Recall the earlier discussion. We have intersection points where we have W state of 3 ensembles, right? Here we have 4 resonators, and at this intersection point, we have population in all 4 resonators. So it evolves into W state. Again, I mean, it is purely quantum mechanical feature. There is no analog of this thing in classical harmonic oscillator. Okay. One thing which I must mention here that, you know, when you are doing experiment, there are all sorts of noises there. For example, photon can leak through the cavity, right? You are assuming coupling, for example, if I go back, you are assuming the coupling with of the resonator with the bus to be ideal. That may not be. And then the 2 resonators can interact with each other. There could be a noise introduced due to the interaction between R1 and R2. So all these things play a very important role in the dynamics. So we can calculate basically the fidelity for the system. And then another thing, we assume some initial condition for the system. For example, 1, 0, 0. That might not be true. There could be some noise in the system. So we did an attempt to incorporate all these things. So this is all ideal. Okay, so here we talk about the dynamics of the multipartite entanglement. When we have finite, for example, this picture B shows the effect of finite lifetime of the photon in the resonator. You know, if you have one photon inside the cavity, it will not stay there for all. It will eventually die down, right? So typically we do experiment within the decay time of the cavity. So what if the photon is leaking through? So notice over here we have black curve, red, and blue. So black corresponds to kappa 0. So we obtain maximum fidelity over here, right? For example, 1 over here, or for some value of interaction time. It goes down when we have kappa, for example, 0.25 megahertz or 0.5 megahertz. There's nothing but the damping of the field to the cavity. So you might be wondering why oscillations here. So basically, you know, there could be interaction among slight interaction that can give rise to these oscillations. Okay, in this basically this second plot, what we have shown, what if the coupling is not homogeneous? Remember, we assumed so far that the coupling of resonator R1, R2, R3, 4 with the bus is homogeneous, right? All G. But if they are inhomogeneous, then again it could give rise to decay, for example, to noise basically in the system. So this contour plot shows then when G2 or G1 is equal to 1, look at this region. So they almost we have 0.99, right? Maximum fidelity. But as inhomogeneity increases, this entanglement also, fidelity also decreases, meaning entanglement is affected due to the line. So here we talk about the effect of the leakage of the photon through the cavity and inhomogeneities of the coupling state. But then you can also ask, what if these resonator, they can also mutually couple? You know, we have resonator R1, R2. What if they're mutually interacting? And it is quite possible. So here we study in this picture effect of direct resonator coupling, which is represented by GM. When kappa is 0 megahertz, fidelity goes to 1. Notice here we are plotting G over GM multiplied by 100, right? So when it is 1, it means coupling is 100 times stronger than the mutual resonator to resonator interaction. However, in the real system, we have a mutual interaction that leads to the decrease in the fidelity. And then the last thing, what is the initial state is mixed, right? We are assuming that there is no noise. We catch photon with perfect probability, so 1, 0, 0. But in reality, there could be noise. If that happens, then again, it is going to affect the fidelity. Theta is the parameter that defines how pure our state is. So, for example, in this case, over here we have fidelity is 1, but as mixing increases, fidelity goes down. Okay, so to conclude, I think this very, very simple system of an arrangement of coupled cavity offer the possibility to study some very interesting features like excitation transfer in distant resonator, generation of this multipartite entanglement, and many more. And I believe that this system can play an important role in distributed quantum information processing. Okay, so thank you very much.
Thank you, Dr. Shahid Qamar. There is one question in the chat. So the question is, does these resonators can be used in long distance communication?
Sure. Definitely. I mean, the idea is to make an whole array. You know, if you're going for real quantum computing business, we need to have a whole mesh of these things so that information can go from one node to another. So the dream of all this study is to eventually have a system where we can have a whole scalable system. It is scalable, by the way, scalable system where we can go from one node to the other node and communicate between these, right? So yes, answer to the question is that is basically the dream.
So, okay. And I also have a question. So when you couple the cavity, how physically experimentalists couple the cavities? Like they couple through some electric field, or like is there a phenomena they can use?
Okay, so as I mentioned that in recent years, there's a lot of interest on this artificial atom. So on artificial atom, it is just like transmission line, right? I still remember the experiment which I did in my MSc. So there used to be transmission line, and we have all these gadgets over there, and then they are coupled to each other, right? To electronic circuit. So the dream is to do quantum optics on a chip. So all these things will be obviously embedded over there, and then we'll be controlling through external. Typically, they are superconducting, right? So we'll be controlling the extra parameter. So yes, indeed, they will be physically connected in this cavity, the transmission on transmission on artificial atoms. Yes.
Okay. And there is one more question. So the question is, how does one decide it on the size of the cavity? Because here there are 3.
Okay, so as far as these artificial atoms are concerned, I must have a. I don't have that view graph. So yeah, thanks to this amazing progress in nanotechnology, right? So they are really very, very small kind of circuits where using this lithography technique, they design on a chip. So the point of the radiation field that we use over here are in the microwave region. Please notice this thing, right? So all these are through microwave. So yes, indeed, they are of I think nanometer scale, so very, very small, very small. I'm sorry, I don't have the exact number, but yes, when they are embedded on a transmission line, they are of the size of 100 of nanometers, something like that. Right? And
Okay.
as far as the these cavities which were introduced by Professor Harosh and Professor Walther, they were of a few millimeters size. Those cavities.
Okay. Okay. Thank you so much. So with that,
Thank you very much.
we can,
Thank you very much.
yeah, thank you. We can